Okay, so now we have shown how theorem A prime implies theorem A. So let's prove theorem A prime. So that will be the third part of this talk. And we have to construct the family psi. So psi is a 6-parameter family of surfaces in B3. The construction will consist of 5 steps. Before I introduce the 5 steps, let me sketch the summary. So first, it will be a collection of surfaces, right? So first, we consider a simpler collection of surfaces called 5-4. So it would be the collection of all translations and scaling of the settled surface, given by the equation x squared minus y squared plus z equals 0. So you have this settled surface, so it's in R3. So it's in R3, we scale and translate it. We even allow the scaling factor to be 0, actually, as we should see. And then we intersect it with the unit 3 ball. So that becomes a family of surfaces in the unit 3 ball. And then we rotate all these surfaces. So originally, if we just consider translation and scaling, so translation gives us 1 parameter, sorry, 3 parameter, and scaling gives us 1 parameter. So 5-4 is a 4-parameter family. And then we rotate, and that will give us, in fact, there will be a 7-parameter family of surfaces. So we will soon see why that is the case. And then we see that actually 5, 7 does not quite work if you just rotate the surfaces. We have to somehow desingularize the surface. And this will give us another family with the singular surface desingularized. And then we finally rotate those. And yes, and that will be what we look for, this family of surfaces here. Okay, so let's start describing the construction. In step 1, we can parameterize the set of all translation and scaling of the set of surfaces as follows. Oh, so one thing first. So we even allow the scaling factor to be 0. So what surface do we get, right? So this is the original equation. If we scale it by a small number epsilon. So this is how we how the formula transform, right? And then we take epsilon goes to 0. The equation we get is x squared minus y squared equals 0, which describe 2 planes, right? 2 planes intersecting. Moreover, we allow the scaling factor to be plus or minus infinity. And of course, like we can translate them. So that will give us planes, just planes, because if you like blow up a piece of smooth surface, like the settled surface, you get this plane, right? Get a tangent plane to the settled surface. The parameterization of this family of all translation and scaling of the settled surface is given by this formula. Okay, in fact, it will be parameterized by RP4. Okay, and the parameterization is this. So we look at the linear combination of x squared minus y squared of x and y, okay, and z, and then the constant term. So you take an arbitrary linear combination of those terms, and then you get you still get a set of surface. So it will be a translated and scaled set of surface. And this set of surface that then you intersect it with the unit 3 ball, and this gives you a family of surfaces in the B3 parameterized by RP4. And then a small remark is that one can check, in fact, like this is a false rebound. Okay. So after that, we add in rotations also. Rotation is given by the S03 special orthogonal groups, right? So we take any element A in RP4 will correspond to a surface in B3 via phi form, and then we rotate that surface by Q inverse. Okay, so Q is any arbitrary element in SO3. Okay, so we rotate it. And because SO3 is three-dimensional, this family phi 7 that describes the collection of all translated and scaled and rotated saddle surface. This family is a seven parameter family. 7 is 4 plus 3, right? So this is the new family. So this is phi 7 children. But notice one thing, that is phi 7 children has lots of repeated surface. So the reason is because the saddle surface has a D2 symmetry. So D2 denotes the dihedral group of 4 elements. It has symmetries. So what are the symmetries? So for example, if you rotate the saddle surface about the z-axis by 180 degrees, you still get back a saddle surface. That means phi 4a. Okay, that means if you take a saddle surface, okay, so this one, let's say this saddle surface, it will be an element in phi 7 tilted, right? But if you take a Q, that is just the Q that denotes the rotation about the z-axis, you get back the same surface. But you have two different sets of A and Q that describe the same surface. So this is what I mean by the phi 2 to 7. It has lots of repeated elements. In fact, there are other symmetries of this saddle surface here, right? So although it is not apparent from the pictures, but there is an axis, this axis, so that lies on the xy plane, so that if you rotate the surface about this axis by 180 degrees, you get the same element. And similar for this this axis here. The conclusion is everything, like almost everything in phi 7 tilde is like repeated 4 times. Okay, because because of this D2 symmetry. And this redundancy, it will cause a problem because we want a 6-sweep out, right? This is a goal. The goal is to have a 6-sweep out. And in fact, the redundancy, the repeated surfaces will prevent us from doing that. So what should we do? We want to get rid of those, repeated elements, right? The most natural way to do it is that we mod out those repeated elements. We take a quotient on the parameter space, right? So originally the parameter space is RP4 plus S3. We can define an action, a D2 action on this parameter space that captures the repetition. In other words, for any element G in this dihedral group, G of AQ will give us the same surface as AQ. So we can define such action, D2 action, okay, that captures the repetition. And then we take the quotient. So this new space X is the quotient by that action, okay. This reduces the family phi 7 tilde to some family, like a more efficient parameterization, denoted phi 7. Okay. So note that phi 7 contains exactly the same surface as phi 7 tilde. It's just a more efficient parameterization. Okay. And quotient is actually crucial for us to obtain a six sweep out. But still, we have one problem. This phi 7 contains singular surface because as we defined, as we recall, we allow the scaling factor to be 0. So if we scale the saddle surface by 0, it's like doing a blow down. So we get 2 planes and it has a singular lines. A singular line is not allowed because we only allow in our space. In this space, we only allow surfaces with finitely many singularities. Okay, the line has infinitely many singularities, so it's not allowed. Therefore, we want to, in some sense, desingularize the intersecting lines. So in fact, a 5-7 would allow one to do ungramped min-max theory, but ungramped min-max theory does not have it does not give a genus control on the minimal surface attained. So we want to do some min-max theory, and for that we need a surface to have at most finitely many singularities. So we have to desingularize the surfaces. That brings us to step 4. In the 4th step, we actually desingularize the surfaces. So how do we desingularize it? So we call, this is the expression for 5-4. So we first desingularize 5-4 and then we desingularize 5-7. Okay. So let us fix a very small number, epsilon, positive epsilon, and then we define 5-4 epsilon by changing the formula slightly. So note that we inserted a term, epsilon z cube here. So it is no longer the set of all saddle surfaces. Instead, it's like cubic surface, right? So for cubic surface, we can have we may get a surface with genus 1 or genus 0. So these are some pictures of the surface that is possible to appear. Okay. Note that we no longer have the singular line because originally the singular line is given by like this x squared minus y squared term, right? So if you ignore all these terms, so if you assume a1, a2, a3, and a4 to be 0, then you have x squared minus y squared originally, and that describes an intersecting two planes. But now you have a cubic term that no longer describes an intersecting two planes. So this is how we desingularize the surface. So after we desingularize the surface, we do what we did. We do the exact same step as in step 2 and 3. So in step 2 and 3, we rotate the surfaces, right? So we rotate them now. We rotate the elements of 5-4 epsilon, the desingularized elements. So we rotate them, and then we mod out the symmetry also. We take some quotient of the D2 action on using the D2 action on the parameter space X. And then we define a collection, a new collection, which is a 7 parameters collection family of surfaces, 5-7 epsilon. So yeah, so it is 7 parameter family of surfaces in B3. And those surfaces must have only finitely many singularities. So this requires some calculation. So we have to show that like surfaces in this form have only finitely many singularities, but this is elementary to do. And moreover, they have genus 0 or 1. Okay. And finally, we also need the area bound actually. So you remember this space we consider. We put a 2 pi. So we want to look at only surfaces with area less than 2 pi. So we have to check that every surface that psi parameterized has an area less than 2 pi. So this is quite a lengthy computation, in fact, but it can be done. It's a lengthy but elementary computation. So we have shown, okay, but we have not actually like shown, but I mean, this is the consequences that psi will lie in this space, okay? Is parameterized only surface of genus 0 or genus 1 and the area being less than 2 pi. So this will be our psi. This is the psi. Okay. And we have to check also that it is a 6 group up. So this will be, so this is in fact some quite lengthy but elementary computation in algebraic topology. One can show that the phi 4. So where's phi 4? So this is the phi 4. Okay, here it is the parametrization of all translation and scaling. So phi 4 is in fact a false speed bump. And then if you add in rotation, you get a 6 speed bump actually. And this is our side basically. So as desired. And this completes the sketch of the proof of theorem A prime. Okay, and using this part here, we complete the sketch of the proof of theorem A, which is about the topology of this space here, and that the first to the sixth cohomology groups are not trivial. So finally, let me mention some further direction to investigate. So if we fix a K, in order to get a K speed bump, so what is the genus of the surface we need? So for example, if K is 1, 2, or 3, or 4, we can get the force speed bump using only genus 0 surfaces, which is due to this family. Okay, so this is a collection of all set of surfaces, right? So when you intersect them with a ball, the unit ball, you get genus 0 surfaces, and you can show that that is a force speed bump. And if case 6, and then theorem tell us that theorem A tell us theorem A tell us when case 6, we can use only we can merely use genus 0 and genus 1 surfaces. But how about for other case, right? Okay, so of course, now fix a K. One can cook up K speed bump using algebraic surfaces. That means like zero set of polynomial equations. But one have to guarantee that they, like the family you get does not contain like singular lines and contains only finitely many singularities. And then the degree of the polynomial will help us to bound the genus of the surfaces, right? But to get an optimal value for the lowest possible genus, like for this question would be challenging. But what's the optimal value? So for example, one can ask like also, does there exist a phi speed bump of genus 0 surfaces in B3? Okay. Of course, we allow finitely many singularities here. So if you think about so we can also, if the ambient space, let's say, is S3, we will not be able to use only genus 0 surfaces that are smooth to cook up a phi speed bump because of the Smell conjecture proven by Hatcher. Right? Because the space of all smooth two-sphere in three-sphere is only an RP3. Okay, so, but what if we allow like singularities, right? And finally, we conjecture that the minimal surface in theorem B has genus 1, index 5, and only one boundary component. So there is an open problem that there's a conjecture that says the only minimal surface with index less than or equal to 4 are the critical catenoid and the equatorial planes. Naturally, one would guess like the minimal surface B, in theorem B to have index 5. And moreover, we are unsure if this minimal surface is the same as the one constructed by Carlotto, Franz, and Jules. So they also constructed a they construct many minimal surfaces, and one of them has a genus 1 and with a dihedral symmetry, D2 symmetry. And we are unsure if this is the same as theirs. So this is also one open question. Yeah. Yeah, so this is the end of my presentation, and thank you very much for listening.